Hey everyone, and welcome to this explainer. Today, we're diving into something that's just absolutely crucial, using deep learning to map devastating floods. See, we have all these amazing cutting-edge AI models that can spot water from the sky with pinpoint accuracy, but, well, there's a massive kind of hidden problem when we actually try to take these models out of the pristine lab and drop them into the messy real world.
And I mean, the stakes literally could not be higher here. Get this, between the years 2000 and 2009, floods accounted for a staggering 38.7% of all natural disasters globally. We are talking about events that affect hundreds of millions of people. When a disaster of that scale strikes, human responders need accurate, real-time maps of exactly where the water is so they can allocate rescue resources and, actually save lives. We desperately need this technology to work perfectly in those critical moments. Okay, let's dive into this. Why can't our absolute best AI actually map floods out in the field? It's kind of the central paradox of our explainer today. We've got this incredible AI that completely crushes academic leaderboards. It boasts near-perfect accuracy scores. But then, when humanitarian organizations like UN Spider or the Red Cross try to deploy these models in actual disaster zones, the AI just fails, or sometimes it literally can't even run at all. So, here's our quick roadmap for today. We're going to cover 1. The AI deployment gap, 2. Designing the FloodLite benchmark, 3. The knowledge distillation myth, 4. The INT8 quantization trap, 5. The winning edge model, and finally, 6. Real-world blind spots. Let's get right into it. All right, part 1. The AI deployment gap, academic triumphs versus field realities. Because as we're about to see, what wins a gold medal on a theoretical leaderboard doesn't always survive in the mud. You can kind of think of these massive academic AI models like Formula One race cars. Take a popular academic model for flood mapping, one combining UNet and EfficientNet B7. It has roughly 63 million parameters and needs 50 gigaflops of computing power. It requires a perfectly paved track. In the tech world, that means massive cloud servers and flawless high-speed internet. But in a disaster zone, responders are using rugged off-road equipment. They're relying on offline laptops, constrained CPUs, drones, and super intermittent power. You just cannot drive a Formula One car through a flooded, muddy jungle. We need models that actually fit on the devices these responders have in their hands. Which brings us to part 2, designing the FloodLite benchmark. Think of this as the ultimate reality check to see if these models are actually tough enough for the front lines. Let's move to and see how this builds. The researchers essentially set up this brutal 4-stage gauntlet. First, they train a massive teacher model. Second, they try to train tiny, lightweight student models. Third, they push those small models through a compression process called INT8 quantization. And finally, step 4, they benchmark them. But not on massive cloud servers. They test them on commodity hardware, specifically an Apple M2 laptop CPU and an in-browser WebAssembly engine, which perfectly mimics the offline and citizen science tech actually used in the field. Okay, part 3. The knowledge distillation myth. This is our first major plot twist, where everything we thought we knew about training small models gets turned completely upside down. So in the AI world, there's this really popular technique called knowledge distillation. The general idea is you take a massive, super smart teacher model and you have it teach a tiny student model. You're trying to transfer its dark knowledge to make the little model smarter. But here is the shocking truth the researchers found. Trying to compress that massive teacher model into the small student models actually made the AI perform worse. Yeah, as you can see, it's strictly underperformed compared to just training the small model totally by itself. Crazy, right? So what does this all mean? Why did this happen? Well, it turns out those lightweight student models were already smart enough right out of the gate. They came pre-trained on this massive dataset called ImageNet, so they already knew how to detect basic edges and textures. And the flood dataset they were tested on is actually pretty small, just 663 images. The models were already hitting a performance ceiling of about 0.93 accuracy. Because the student was already so capable on its own, the extra input from the teacher wasn't providing any magic dark knowledge. Actually, scratch that. It wasn't just unhelpful, it was injecting confusing noise. For the best tiny model, called MobileViT-XXS, the teacher's help literally degraded its performance. Moving right along to part 4, the INT quantization trap. Since the teacher wasn't helping, the researchers had to rely on physically shrinking the models. Let's look at how to do that safely. You can't just blindly shrink an AI model down and expect it to work perfectly. The most common way to shrink one is called INT8 quantization. Simply put, this strips a model down from highly precise 32-bit decimal numbers to much simpler 8-bit whole numbers. It radically shrinks the model's file size so it can actually fit on a tiny device. But doing this is essentially like taking a beautiful, high-definition photograph and compressing it into a super pixelated GIF. It's a highly dangerous process for the AI's brain.
Now, what's really interesting about this slide is looking at just how catastrophically one of these models failed. The MobileViT-V3 model started with a totally solid accuracy of 0.926, but after quantization, total collapse. It lost nearly half its accuracy. Why? Well, it uses this mathematical function called hard swish, which is unbounded. So when it looks at highly reflective floodwaters, its internal numbers just spike wildly, and that 8-bit compression we just talked about absolutely cannot handle those extreme spikes. But look directly below it at efficient netlight 0. It barely lost any accuracy at all. That's because it uses a bounded function called ReLU6. It strictly caps its internal numbers at 6.0, making it incredibly stable when compressed.
All right, part 5, the winning edge model. By carefully dodging that teacher model myth and surviving the quantization trap, the researchers finally found their champion. So we finally found our Goldilocks configuration. As you can see, the INT8 Efficient Net Light 0 model is just the absolute sweet spot for field deployment. It's 3.8 times smaller than its uncompressed version, weighing in at a tiny 5.2 megabytes. And because it's so small and stable, it absolutely screams along at 58 frames per second on a standard laptop CPU. Best of all, it recovers 95% of the massive teacher model's accuracy, but it can actually run entirely offline, out in the field, right in the hands of a first responder. That's a huge win. But hold on, we can't declare total victory just yet. Let's hit part 6, real-world blind spots, because even our incredibly fast, highly optimized champion model has some pretty critical weaknesses out in the wild. As you'll see here, this brilliantly illustrates exactly where the AI just completely gets tricked. If you look at the hard examples at the bottom, check out the red and blue zones. The red zones, those are false positives. The AI gets totally faked out by sun glare on wet asphalt or shiny roofs, and it thinks they're flooded rivers. And the blue zones are false negatives. The AI completely misses floodwaters that are hiding beneath overhanging trees or tall grass. I mean, a standard camera just can't see through a leafy canopy. And, well, neither can the AI. And there's one more really crucial caveat we have to talk about. The models we've been looking at were strictly trained on close-range drone and ground photos. If you take this champion model and suddenly feed it high-altitude satellite imagery, like the Sen-1 Flood 11 dataset, its accuracy completely plummets. It drops from over 90% down to a virtually useless 16%. It suffers what's called an out-of-distribution collapse. The AI essentially gets altitude sickness. It just proves you absolutely cannot build a one-size-fits-all model. A drone AI is definitely not a drop-in replacement for a satellite AI. So as we wrap up this explainer, the big takeaway for us is that in the high-stakes, life-or-death world of disaster response, raw theoretical accuracy on a leaderboard means absolutely nothing if your model can't even boot up on a dusty laptop in a flooded command tent. Stability, bounded mathematics, and off-grid efficiency, that is what actually saves lives. We have a champion for drones today, for sure, but as we keep pushing models to run in web browsers and on smaller and smaller devices, we have to ask ourselves, when the next generation of AI hits the edge, is it going to be built for the perfect conditions of the lab, or will it actually be tough enough to survive the messy reality of disaster response? Thanks so much for learning with us today.